Let's now look at the intermediate value theorem and walk through some examples. Here's the main idea of the intermediate value theorem. If you have a continuous function that goes from one value to another, it must pass through every value in between. I've written the intermediate value theorem here in our green box, and we're going to go through it and at the same time look at our graph so that we can better understand it. Our intermediate value theorem has a condition, and that condition is that our function is continuous. In other words, our theorem only applies to continuous functions. If our function is continuous on the closed interval from a to b, looking down here at our graph, we are going from x is equal to a to x is equal to b, and n is any number between f of a and f of b. I've already highlighted it down here, and it lies between f of a and f of b, and those two functions can't be equal. Then there exists a number c, which I've highlighted right down here, in the interval between a and b, such that f of c is equal to n. Let me tell you exactly what this means. All this means is if all these conditions are met, then we have a number n that's equal to f of c that can take on every value between f of a and f of b. Let's now see how this works in practice and walk through two examples. One really nice application of the intermediate value theorem is when we can use it to show that an equation has a root in a specified interval. And that's what our examples are going to be about. In our first example, we are going to use the intermediate value theorem to show that there is a root of the given equation in the specified interval. Let's talk at first about what a root is. A root of this equation is just a point x where x cubed minus x minus 2 is equal to 0. So basically, when we solve this equation, we are just finding the roots. I have graphed this equation so that we can better understand this. What we are looking for is to show that we have a root of this equation. So that is going to be this point right here, where our function x cubed minus x minus 2 is equal to 0. And we want to show that we have a root between x is equal to 1 and x is equal to 2. To show this, we are going to look at our function values at 1 and at 2. F at 1 is equal to 1 cubed minus 1 minus 2, which is just minus 2. And let's make a note that that's less than 0. And then f of 2 is 2 cubed minus 2 minus 2, which is 8 minus 4, is equal to 4, which is greater than 0. Because f of 1 is less than 0 and f of 2 is greater than 0, the intermediate value theorem tells us that there has to be a number c such that f of c is equal to 0, because our function has to take on every value between negative 2 and 4, and 0 lies between negative 2 and 4. So by showing that f of 1 is less than 0 and f of 2 is greater than 0, we've basically shown that the intermediate value theorem will guarantee that we have a root between 1 and 2. Let's now look at our second example. This example is similar to our first example, but a little bit more complicated because we are not given an interval. In this problem, we are asked to show that there is a root to this equation. We're going to solve this problem in 2 steps. Our first step, we are going to create f of x. Because we want to find a root to this equation, our function f of x is going to correspond to f of x is equal to 0. So if we go up here and look at our equation, we can write this as the square root of x minus 5 minus 1 over x plus 3 is equal to 0. And this is our f of x. Let's go ahead and write that down. F of x is equal to the square root x minus 5 minus 1 all divided by x plus 3. Now what we're going to do is we're going to find f of a and f of b, because those 2 quantities are used in the intermediate value theorem, and that's the theorem that we're going to use to show that we have a root to the equation. Now, we are not given a and b, so where do we start? I think the best place to start is to look up at our function and see that we have a square root, and we're going to have to require that anything inside our square root is greater than or equal to 0. So that's where we start. We are going to set x minus 5 greater than or equal to 0, and that tells us that x has to be greater than or equal to 5. We now need to choose an a and a b, and it has to be greater than or equal to 5. I am going to let a be equal to 5, and let's see what happens. F at 5 is the square root of 5 minus 5 minus 1 divided by 5 plus 3. So this is equal to minus 1 over 8. And let's make a note that that is less than 0. Now we need to choose a b. We just need to pick a number that's bigger than 5. Notice that the answer that we just got was minus 1/8. That's really close to 0. So I have a guess that we could make b be equal to 6, and we might get a function that's bigger than 0. Let's see what we get. F at 6 is the square root of 6 minus 5 minus 1, all divided by 6 plus 3. This is 1 minus 1/9, and this is equal to 8 over 9. Let's highlight that. This number is greater than 0. So this is great. We found that f of 5 was less than 0 and f of 6 was greater than 0. So this tells us by the intermediate value theorem, let's write that down, we'll abbreviate it as IVT, there is a root to this equation and let's put in parentheses that that root is where f of x is equal to 0, since f of 5 is less than 0 and f of 6 is greater than 0. The intermediate value theorem tells us that our function is going to take on all the values between f of 5 and f of 6, which means it's going to take on the value of 0, which is a root to our equation.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.